So on to the next speaker for us today. Matt Cochran is a software engineer with 20 years of experience, and he's currently director of engineering at the Trade Desk. They also happen to be a sponsor, so we can thank him twice for being a presenter and a sponsor. So Matt, the stage is yours. Thank you.
Good afternoon, everyone. My name is Matt Cochran. I'm from the Trade Desk. I'm director of engineering for our data engineering team at the Trade Desk. We are an advertising technology company. Today I'm going to talk a little bit about how we grew into needing a cold store, how the environment that we operate in, kind of the industry and the reasons why we need to do these things. And then I'm going to walk through a little bit about some attempts we made to build this on top of Cassandra and some of the things that we've learned from that, some hard lessons in there. And we're going to talk through a little bit about discussions we've had with Aerospike and changing our approach to use the Aerospike platform for doing what we needed to get done. So advertising technology. Advertising is an old game, right? We in the last century, we had print advertising. The whole idea is for an advertiser to reach a target audience with a message that says, hey, come buy my product. Or here's a compelling reason why you should look at my products. Publishers love to do this because in return, they get paid to show these advertisements. That supports journalism, supports all kinds of good things in the world. So you kind of need a way to transact that as you get more and more sophisticated into digital forms of media. So what's developed over time, when digital media first came onto the scene, things were still kind of transacted the same way. So an advertiser might go to a publisher and say, we'd really like to buy some ad space. Or a publisher might come to them and say, hey, you really should try advertising on our site. It's very cumbersome, and it's also very indirect. It's one of those things where you don't really know who you're advertising to. If you know a little bit more about your demographics, if you know 20% of my population is from the East Coast and 10% is from the Midwest and so on, then it gets a little more interesting. And that's kind of a game that we've always done as far as advertising goes. That's how newspaper distribution used to work, right? They would tell you the number of subscribers they had and things like that. But when you get into the digital world, things become a little more discrete. So what happens is, the industry has kind of moved over time to a transactional model where when a page loads from a publisher, they work with a company we call an SSP, or supply-side platform. And what the SSP does is they try to help the publishers find the best ads for the publishers, ones that pay well, ones that meet the criteria. You can think of the New York Times, for example. They want to show a Gucci ad, right? Because that's commensurate with the stature of the New York Times. So they also help them kind of curate the advertising that happens on their site. So there's a lot of work to do there. But the SSP really is focused on supporting the publisher. And so while they have an exchange, the advertisers need to somehow participate on that exchange. And so they would like to buy those ad spots as those pages are loading so that they can reach their target audience. But they can't handle that volume. If you think about all of the page loads that happen across the internet all at the same time, it's massive. Trust me. So the way that this real-time exchange is developed, but advertisers couldn't take advantage of it to buy the impressions that they felt were more valuable to sell their products. And remember, too, that's the side that has the money. That's the side that's trying to buy these things. And so if they're not getting what they want, then it gets there's a little bit of conflict in the market. So that's where we came in. So we are a demand-side platform. What we do is we actually integrate with the SSPs, the individual exchanges, and we get in the requests for a bid. And so basically what happens is they will say, hey, here's a page load that's happening right now in the New York Times. It's a sports page. What would you give us to show an ad right now? So what our job is to do is to help comb through our set of agencies or advertisers that are advertising on our platform, all of our ad campaigns, and see which ones might be suitable for or might desire to buy this piece of inventory, this page load, this space on a page load. So when we do that, we're looking at two dimensions. We're looking at the situation of the data, like the New York Times, the sports page, the time of day. Those are situational things like that are happening right now. But we need to combine that with data. Say we use a system of anonymous IDs where we can say, hey, this ID might be interested in buying a car, right? And so that informs the advertiser and lets the advertiser make an even better decision on who to show an ad to. So pretty straightforward, except with all of those things in that chain, again, we're trying to beat the page load, right? So you're looking at a page, we're trying to get there and have the ad be there by the time the page finishes loading. So when all of that happens, we end up, there's a set of chain here, and by the time we get to the end, we're stuck with, we need to respond in 20 milliseconds. Okay, so we need to be able to figure out things very quickly. We need to be able to make a decision. We need to understand the value of what we're trying to buy, and we need to take action and do it right away. So data is crucial in that evaluation, right? Data lets the advertisers get the most value for what they're trying to do, right? Why buy an ad spot and show it to somebody who's not looking for a car, right? If they're not interested, they're not interested. Don't do it. Don't waste your time, right? It's okay. Don't waste their time, right? So what we've done is we work as a kind of a platform. But when we get all of those bid requests in, we only have those 20 milliseconds to respond. And that seems pretty cool, right? That's a lowish latency, not microseconds like in the financial industry, but it's lowish, right? That's pretty cool. But we have to do that 10 million times a second. That's fun. That's just and I've seen it grow through the years, and it's just been amazing to watch, right? It's like, wow, this is even getting crazier than last year. This is amazing. So we need to be able to process those consistently, accurately, in depth. So we need to be sure that we are not missing opportunities 10 million times a second. So when you add data into the mix, there's a whole ecosystem of marketing providers and data providers out there in the world. And they're doing analytics on activity they see on partner websites and things like that. For example, if you go to Auto Trader, they'll say, hey, you might be looking for a car, right? Okay, that's fair, right? Simplistic case. But this ecosystem of third-party providers is growing. And as it gets more and more complex, or more and more participation, they needed to be able to have a platform to sell their wares, basically, right? You can think of it as a set of shelves, right? Or a set of shelves in a grocery store, and there's a list of data products, and an advertiser might pick this one and that one, and let's do the combination of these two, and those kind of things. And so all of these people, or all of these companies, want to use our platform as a way to offer their products to more customers. So there's some interesting things here too with the traffic. So when we get those requests for bid, we are getting those real time in from SSPs that are close to those data centers. So again, it's server to server, right? As far as the browsers to their servers and from their servers to ours. So it's better for us to be co-located or closer to their data centers. So it doesn't have any real, an SSP can put their data centers wherever they want, right? And we have one close to them. But in the end, a data record might come in, an anonymous ID record might come in one data center, and it might come in another data center all the way around the world. It just happens that way. So so all of those data segments that we're getting off those shelves, all of those need to be distributed around the world to be wherever they are when the request comes in. So we have to kind of anticipate. So, and remember too, we're doing this 10 million times a second. So these segments can get expensive. If the records grow too large, and as we get more data partners to fill up those shelves, the size of those records can grow, and the larger they grow, well, that becomes a problem of CPU, because at some point you need to choose which ones you're going to keep and which ones you're going to let go. And so when you do that evaluation, you're burning CPU. If you're doing that, so we have to be careful with that size because we're optimized for read, right, too. So we need to make sure that when we read that and deserialize and serialize or deserialize those records, that we're not consuming too much CPU to where we can't make those decisions quickly. Sorry. And then there's 50 billion of them. So it's a little challenging. I know it's a little more, but. So this platform for data, they do have to send us this data in advance. So regardless of whether a data partner has a customer for the data, they need to be able to send it to us because it needs to go up on the shelf, right? And so if they have to send it to us in advance, otherwise when the customer goes to use it and it's not there, they don't want to wait a week to say, oh yeah, we'll start sending it to you, right? Well, it'll be there, right? You don't want to do that. What you want to do is you want to have it ready, you want to have it in place. But then not all that data is used. So then in our hot stores, in our data centers, we have the problem of we have a lot of data that is just waiting to be used. And it's not immediately useful. So we get about 100,000 queries per second of this data. And each query can add one segment or more to one or more IDs. And so there's different data partners that have different behaviors. And so we have to kind of manage those behaviors. They're doing big batch processes, and then they'll send us a chunk of data all at once, and we need to be able to absorb that in a reasonable way. So there's another dimension of operational needs there. But in the end, all of those updates, they turn into about 20 million TDID targeting data or a segment ID pairs at a second. So it can get pretty voluminous. If we are on a data center specific or a data center centric model, then each data center then has to do that same work. Because again, an anonymous ID record can show up in any given data center, right? And so if we're going to duplicate that CPU utilization across that, then it's not really as efficient as it could be. So the idea was that what we wanted to get to was a cold store. So for all of this data that's up on the shelf, it stays in the cold store until it's needed. For all of the IDs that come in that aren't in a data center, they stay safely stored away in the cold store. And so we have two cases. Frozen TDID case. So these can come and go from data centers. You might be seen in one, depending on the publisher SSP relationships. You might be seen in another, depending on those relationships, right? And so what you want to do is you want to be able to take the data from the cold store, the whole user record, and get that to the hot caches when it's needed. So it's kind of a classic hot-cold cache concept. Nothing revolutionary there. Now the real trick is that on those records, you have a list of these segments. And then when those state changes, when it goes from used or from unused to used, you want to be able to distribute those out quickly so that you don't miss more opportunities when customers are expecting those, right? So how do you keep only the actively used segments in the environment, or in the hot data centers? And then how do you thaw those segments? So we have two kind of patterns that we're trying to solve here. Whew, Cassandra. We'll do it. So we were intrigued by the intake rates. Write load's amazing, right? It's alluring. We can stream data to it. We can load it as fast as we can. We're not too worried about reads at this point. Let's see if we can get it loaded, right? So we spoke to a team at a popular video provider about it, and we said, how does that work for you? And I should have known better when they said, oh, it works great, blah, 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 blah. And then, what do you guys know about Aerospike? I just should have listened. So we had a great conversation at any rate. One thing I don't think I touched on, I just missed. We've been using Aerospike as our data center hot cache or a hot store since 2011. So we're very familiar with the technology. We're very familiar with the company. This is something that we've been using for longer than I've been at the trade desk. So we're very comfortable with it. But we decided to take a look at this because those write rates are pretty intriguing, and we never got that kind of write rate before out in Aerospike. So what we were trying to do here, so in order to support those write rates, is we had to change the way that we organize the data. So we had to go, instead of from the Aerospike approach of a record with the data on the record, all the data on the record, we had to go to the compound key of the TDID along with the segment ID and some metadata as part of the record. It's the only way we could figure out to get the right speed that we wanted to do. So We're thinking like, again, 20 million a second. Let's see how that works. But most of all, we cannot do read, update, write. Right? We're not going to pull this back to a client and push it back to the server again. And so that's the thing we're really trying to avoid. OK, that gets us to the first use case, because we can assemble a TDID record based on all of those entries. But a secondary index is required if we want to be able to thaw elements. If we want to say, hey, this segment now, I need the whole population of TDIDs that have that segment. So you're going to need a secondary index. The read-write is lower, right, because it's based on customer activity. It's more of saying, hey, I'm using this now, and I'm launching a campaign. That's a pretty intentional activity. But how do you manage that state change? And let's say you have a very large attribute set, and maybe it's 5 billion IDs. And so how do you take those and then quickly distribute those to the data centers? And then how do you even write that on a disk? Right? That's kind of a little rough. So we've got use case 1 going. And what we learned was CPU is everything in Cassandra. Basically, when we have more repetitive updates, and we do sometimes with some data partners give us some jitter on keys and things like that, it means lots of compaction, right? And you're always kind of trying to scroll those tables back down to the accurate data, the latest data. So compaction means CPU. You got to have compression. You know, the storage requirements get too unwieldy at the size we're operating, so we have to have some compression. That's more CPU. It's Java, garbage collection. So even the optimized versions, it's still CPU. So really, the question really, or the thing that we really learned, you know, kind of bitterly a little bit, was that in order to make this work, you have to have a ton of CPU for a relatively small amount of data on a given machine, which means that the number of machines gets out of hand very quickly, right? Also, there's some nuance there too. When we do the compound key, we get a lot more data skew. Some machines saw like 2 to 3 times more in some spots, right? And so that just causes cascading performance problems and things like that. It becomes a whack-a-mole problem, as I think we found out. So, little challenging there. On the second use case, the functional problem that we found is we tried to build secondary indexes or some alternative. Interestingly enough, we had a data partner that was sending us basically all the IDs, saying these are all blue. They're all blue. Everybody wants blue. Everybody's blue. And we never noticed, because in an atomic operation, it's not that big of a deal, right? Because when we're putting it in the hot cache in Aerospike, it's just record, update, record, update, record, update, done, right? Never even noticed. But when we try to write it all out on the disk, it's like, oh, that's big. You know? That's a lot. So for one category, right? So we considered things like a 2-cluster solution. Let's do the TDID store one way, the other store the other way. Maybe we just end up with 2 clusters. That just stuff. But we did make it work. We did make the use case 1 work. Came out with 500 i3-2XLs, I think is what we ended up at. Yeah, TC what? Well, let me caveat that a little bit too, because the thing is we made it work, but only by turning off replication. Because guess what replication means? It means more CPU. Oh, man. And so basically, we created a set of backups. We have log data on the input side. We can recover if we try, or we can not. We can make that choice. We made that choice a couple times, but 22 million writes a second though. That's not bad, right? And even the reads we got up to an inordinate amount. That's really not bad. I mean, is it worth it? When we're trying to do the math on the size of those nodes, yeah. And then Srini and Tim and folks from Aerospike came to talk to us in January 2018 when we were thinking about this. Mostly because I think they were aghast at the 500 node proposition. But, but we talked through some scenarios, and we drew it up together, and we said, hey, what are some solutions that you might have already that we could leverage, and how could we make this work a little better? We talked through XDR scenarios, but the way that we optimized our storage format in our data centers made that kind of impractical. The secondary indexes, we couldn't think of a solution for that at the time. So we said, let's just talk a little bit, and let's see where we get. And then there were some other features coming out, I think, towards the end of that year that were looking pretty promising. So this is horribly lifted from Tim Fox's presentation to us in October of 2018, and Ronan too. Basically, the idea is, OK, let's rethink the data structure. Let's rethink this a little bit. You guys know, being us, we want the segments on the record, right? And I'll get into that a little bit more. Let's use a map. Pretty straightforward. Here's how it could work. Basically, if we use the map to do that, the users can have all the attributes associated, or we can have other attributes on top of these associated with them in other bins, and then light bulbs started going off in our heads about some other things that we wanted to do. All these segment IDs are on one record. There's no compaction, or there's compaction, but there's Aerospike compaction, which is not nearly as brutal, right? So let's go through and kind of see what we could do. Thaw TDID, yeah, primary key, done, piece of cake. There's no big scan. It's really just give me the record. That's it, right? Writing the segments onto the record, this was clever. This is the part I really liked. So map operations, right? And we just stream it in and let the server filter it out when we get that next feature, but we'll get there. But the TDIDs matching a segment, this was really cool too, because this was the kind of the scanning that we were talking about before, and being able to shard those scans. That was a really cool idea. Still some questions there, but it definitely spawned some ideas. Yeah, it's a lot. 750 terabytes of raw-ish, replication factor 2, fragmentation, so 3 petabytes. Ow, okay. Yeah, and we know it's a lot of data. So with the optimization, Tim and Ronan suggested some optimizations that were pretty clever, and so we could get it down to like 2.3 petabytes. That was cool, ish. And so the way that we had structured a lot of our other applications kind of dictated a drive towards more Amazon infrastructure for this case. And so we're looking at about 150 nodes to support this. That's still too big. So, we have a lot of compression in Cassandra, and message pack was, well, good, it's still not enough, right? It's 150 nodes. Scans probably won't work for that. And we said, guys, it's really compression. I think it's what we all came to, is we got to find a way to do this. So Srini says, give us a month. So we got it in a month. They came back to us in a month, and they said, you want to try it? I actually asked for a pre-release version, but Brian said no. That's OK. That was fair. What we got to with that was we got down to 60 machines. We didn't do the M5 metals. Yeah. So still not super cheap, right? But a heck of a lot easier to manage than 150. Whole lot easier to manage than 500. So I think we're doing pretty good by this point. So while in the meantime, we had been working on the secondary index problem, and we came up with another algorithm to do that. So, which, fortunately for us, works better if all the data is on one record. So, when we started thinking through this, there was those other use cases that we came up with. We started realizing, oh, well, we have a ton of flexibility now. The data is co-located on one user and one record. We can do all these other things that we've been thinking about doing, which is 4 or 5 other things that we really wanted to do. So it started to feel like, okay, we have something here, right? We have something here. So we turned it up. I think April 1st, we eliminated Cassandra, turned it off completely. So we're fully now onto this whole Aerospike cluster. Runs pretty well. Still some things I think we'd love to see, but it's working, right? We have already started improving our ability to target for our customers, which is the key driver for all of this, is to be able to do a better job for them. We can now transfer our data center CPU utilization into the bidding side of the stack as opposed onto the data absorption side of the stack, which means that we can take advantage of more opportunities in the market. Right? The more we process, the more we see, the more we can do. We also inadvertently reduced our AWS egress traffic through absorbing the data in a different location because we were using this model. So we're going to start aggregating third-party data provider requests as well. So that gives us a little better control of that fire hose that we have coming at us every day. In our data centers, since we're optimizing now to storing only the data we need to use, we can store it on more records across the whole stack. So pretty happy about all of this. So that's it. So thank you. I'm happy to answer any questions if anybody has them.
Yeah, how are we addressing those if all the data is in one record?
So on the segment level, each segment is an individual, and so we can do predicate filters to filter them out when we send it back, or we can trim them off when we write, as soon as we have that one feature, I think.
But the TTL is for the entire record, though?
No, TTL is for each individual.
Entry in the map?
Yep.
Oh, okay. Thank you.
Yep. If you think about it, a data partner could set their own criteria, right? This is good for 30 days. This is good for 10, and things like that. So, yeah.
Hi there. Question about the 60 nodes. Was that 60 i3 16X cells, or?
No, we went with the M5 metals.
Got it.
Yep.
And then did you need to replicate this data to a separate cluster sitting in another Amazon facility, or is it all in one? How did that work?
In the cluster itself, like the replication.
Did you need like a secondary cluster elsewhere, or is it all in one location?
So this is all in one location because we also replicate to the data centers.
Got it.
Right.
Okay.
And so there's a lot of moving parts, but yeah.
Thank you.
Yeah.
What block size are you using? What is the maximum amount of segments we can store?
1 meg block size, so quite a few. Thousands and thousands and thousands. So, okay?
All right.
Okay.